This podcast is a project of the Climate Designers Network.
Hey, this is Eric. As we are on hiatus this winter, planning yet another amazing season of Climify, we thought it'd be nice to continue to provide you climate education and climate action, but this time through the work of some of our friends. So today we invited a kindred spirit podcast produced at MIT called Today I Learned Climate to our platform to share what they know about materials. The host of Today I Learned Climate is Laur Hesse Fisher, the program director at the MIT Environmental Solutions Initiative. In this crossover episode, Laur and Elsa Olivetti dive into materials and their impacts on our planet. As designers, we choose materials to build the things we create. So knowing more about how to select, reduce the use of materials and reuse materials, in addition to the knowledge of how to find the right vendors that manufacture responsibly, can help us all become better climate designers. So I hope you enjoy this episode. It's our first time doing this. So let us know what you think about it, because we might be doing it again and sharing wisdom from our other great sister podcasts. Enjoy the episode.
Just the quantity of materials is kind of astounding. I think that's partly what's tricky about any of these conversations around CO2 or materials use, is that the numbers are huge, and how do you relate them to anything that feels more concrete to us is difficult.
Thanks for joining us on Today I Learned Climate, where you learn about climate change from real scientists. I'm your host, Laur Hesse Fisher. Today I asked an MIT professor about stuff. The materials that companies use to build our infrastructure and that we use in our everyday lives.
My name is Elsa Olivetti. I'm the associate professor. Wait, no, that's not right. I'm the Atlantic Richfield Associate Professor of Energy Studies. I work in the Department of Material Science and Engineering here at MIT.
Professor Olivetti studies the impact of materials on our environment and how we can lighten the load.
I was always interested in the broader implications of materials and how they fit into the systems and society, how we interact with them as people. So, for example, if we were to increase electrification of the vehicle fleet dramatically, there would be a significant increase in demand for the derivatives of cobalt. So trying to understand kind of the match between the supply of those materials and the demand for those materials.
And some of Professor Olivetti's work is at the lab bench, where she and her students try to better understand the chemical makeup of materials. This helps them explore how these materials can be used, reused, or recycled. A
lot of times the way we currently dispose of those materials, waste materials from different industries, is either just in a landfill or as volume that would go into roads. And so that's a use, but it's not a particularly high value use, right? So in order to understand how we might make use of those waste materials in higher value or more environmentally beneficial materials, we need to understand what's in there. What is their chemical composition? How reactive might they be under certain conditions? And the innovations that come from this research can be simple, yet pretty impactful. So one thing we make that's pretty easy to wrap your head around is a brick, right? So but it's a brick that's fired at pretty high temperatures. So we make that, the processing of that is upwards of 1,000 degrees Celsius. But if we're able to make use of the chemistry, we can do that instead at 30 degrees C. That's only 86 degrees Fahrenheit. Or a warm day in India, which is where the project is based, so that works out. And so in order to do that, in order to enable that reaction to happen at 30°C, we need to understand how durable is that over time. Is there going to be an issue if there's, in the monsoon season, if there's a lot of water that's uptaken into those materials, those bricks? We can develop a really fancy technology, but if we don't understand what the local context is, then maybe that's not useful. So I've heard you share that materials in manufacturing make up about 1/3 of carbon emissions globally. Mm-hmm. Can you break that down for us? So what's causing these emissions? The majority of it is steel and cement. 25 to 30% is steel, and about 20% is cement. Aluminum and paper and plastic are all about 5%, 5 to 10%, depending a little bit on how you group these things. But there are these big contributors, and so it's just important not to forget that from a mass perspective, that focusing on innovations in steel and cement are always useful. If you want to move the needle on CO2 emissions when it comes to materials, you have to think about those two. After water, concrete, which is made from cement,
is the second most widely used material on the planet. Think of all of our pavement, all of our factories and buildings, bridges and highways.
To give a little bit of a scale, just the quantity of materials is kind of astounding. So I think it's 90 billion metric tons per year of materials. And so cement is, upwards of maybe between 3 and 4 billion metric tons per year.
How can I even start thinking about billions of metric tons? Do you have any way that I can visualize that or try to understand that?
Probably not. I mean, I don't know. We with the project in India, we were thinking about the waste generation that was happening per day in these facilities in terms of elephants. Like, you could sort of think about an elephant.
How much does an elephant weigh?
2 to 5 tons.
Okay, all right. So that's still billions of elephants.
Yeah.
I can barely imagine 1,000 elephants, let alone a billion elephants. That's just such a huge number.
I think that's partly what's tricky about any of these conversations around CO2 or materials use is that, the numbers are huge, and how do you relate them to, to anything that, feels more concrete to us? It's difficult. We're on the orders of billions of metric tons. It's still growing, right? We're still building infrastructure. That's why trying to move the needle on CO2 emissions in that is hard because we're still making a lot.
Okay, so steel and cement make up a majority of where CO2 emissions come from in materials and manufacturing. But why? What causes those emissions?
We're talking about CO2 emissions. The majority is in two places, really, is, the energy to run the factories, the CO2 emitted because of energy generation and the CO2 that comes from the chemical reaction.
To build this out a little, so factories use a lot of electricity to make cement and steel. And the amount of CO2 associated with that depends on what kind of fuel is used to make the electricity. So, like, you in your house may use as much electricity as I do in my house, but if you get your electricity from wind or solar, and if I get my electricity from coal or gas, then running the lights at your house will contribute a lot less CO2. So in addition to that, making cement requires chemical reactions that emit CO2 and other greenhouse gases, kind of like how the chemical reaction that happens in your car's engine creates CO2. So when we look at the CO2 released by making steel and cement, we need to look at how much electricity is being used and how that electricity is being generated, as well as how many emissions are released from the actual chemical reactions.
It depends on what grid you're using, but it's roughly 50-50 between the energy used and then the kind of reaction of the processing associated with that material.
So as you're looking at something like steel and cement, what are the efforts that are underway, either by your team or other colleagues that you know about, to reduce the impact of this?
Trying to use supplemental cementitious materials where we're using a little bit of something in place of a little bit of something else.
So this is using a different ingredient for cement that actually reduces CO2 because there's not as much of a chemical reaction. And because this new ingredient is a waste product from another industry, this also means you're giving that waste an economic value and a second life. Another solution is to use a different material altogether.
Cars is a great example, right? The material that we're making our cars out of. So aluminum requires more energy to make, more electricity to make, but it'll use less CO2 over time depending on how long we drive the car.
That's interesting. It would use less CO2 than something like steel, which is heavier because the car actually takes less gas to run.
Yeah.
So scientists look at both the CO2 emissions from mining and making material, and also the emissions that may come with using the material, like making cars lighter and more fuel efficient. But what happens when stuff is done being used? Well, how easily something can be reused or recycled is largely dependent on how it's made.
As technology has become, amazing and advanced, we increasingly make things more complicated, meaning more elements, which, there's more different kinds of stuff in them, which makes it more difficult to manage at end of life. So we sometimes make the joke that you carry the periodic table in your pocket in your cell phone. And it's not that much of an exaggeration because of the increasing complexity of that. And that's true not just for electronics, but alloys and jet engines. And, the way we have become more and more advanced is typically adding more complexity to them. So I think that that's just another tension in terms of the quantity, is also the complexity, and trying to manage that as much as we can is the challenge we face.
Steel, cement, and reusing materials are huge areas for innovation, and many different groups at MIT and around the world are tackling them. To see some new and pretty creative solutions, check out our show notes on tilclimate.mit.edu. That's tilclimate.mit.edu. What do you want to know about climate change? Do you still have a question from this episode or one of our previous episodes? Let us know. Tweet your question with the hashtag TILClimate or sending an email to climate@mit.edu. Thanks so much to Professor Elsa Olivetti for speaking with us, and to you for tuning into Today I Learned Climate. I'm Laur Hesse Fisher from the MIT Environmental Solutions Initiative. See you next time.
Climify is produced, edited, and engineered by me. A huge special thanks to Ellen Keith Shaw and Christine Pilot for their gorgeous work on the new branding, Atul Rashik and Mark O'Brien for their design help, and Brandy Nichols for her strategic guidance on improving the offerings of this podcast. If you enjoy the work we all do here, and you have a spare minute or two, we truly appreciate if you left a rating and review over at Apple Podcasts. The more folks that review our program, the higher the algorithm pushes up Climify in the search results. And in turn, the more likely we all can learn how to become climate designers.